Happy Monday. I guess that's how out of it I feel. Any questions, needs, concerns, etc. from you guys before we get started? All right. Well, past couple of lectures, we've been looking at angular motion, which is to say rotational motion. We've been, first of all, describing the ways in which rotational motion can be described, namely how all of the original displacement, velocity, acceleration logic we've been using has a direct angular counterpart, namely rotational displacement, rotational velocity, and rotational acceleration. We've also talked about centripetal force and centripetal acceleration, and today I just kind of want to practice all of those things, see how they all mix together in a few ways. So, first thing, we're going to take this information and look at the correlations between the linear and angular worlds, and look at a situation where linear and rotational motion happen to coincide. The main place where that happens is actually just a rolling object, a tire, basically. So, we're going to look at a car that happens to have 4 tires. The number of tires doesn't actually matter, sorry. We're going to look at a car initially driving forwards at 29 meters per second, and eventually the driver is going to hit the brake. When they hit the brake, the car is going to slow down at a rate of 1.75 meters per second squared. Oops. So V initial is 29. A is going to be at negative 1.75. And we have also been told the size of this vehicle's tires. These wheels have a radius of 0.33 meters. That is the radius, that is half the diameter. So, with that information given, our first question is going to be, how quickly are the tires rotating before the brake is applied? In other words, what is the initial angular rotational velocity of these tires before the brake is applied? We know the linear speed of the tires, this is how quickly they are moving forwards, but what I'm wanting here is, how quickly are the tires rotating as that happens? So, we know VI, A, and R, and we want omega I. We need to figure out how to get there. Now, the bulk of the information that we already have is linear, right? We've got linear velocity, linear acceleration. How can we use that to figure out a piece of angular information? Because our old linear formulas only have linear stuff in them, A, V, delta X, and T. Our angular formulas only have angular stuff in them. None of these have normal English V or normal English A in them. So it seems as though these two worlds are kind of separate from each other. We need to figure out some way to bridge that gap. So it's now finally time for me to acknowledge these things in the middle. I don't know if I've mentioned yet. This family of formulas exists to translate linear motion into its corresponding angular counterpart. Since we're looking at a wheel, I'm going to once again grab the disembodied bike tire of science and demonstrate that while this thing rotates, it does roll forward at the same time. So that means that its rotation is directly tied to its forward motion, correct? And the distance it rolls forwards depends directly on how many times it spins. If it spins more times, it rolls further forward. So the two worlds are related. For a rolling object, they do have something to do with one another. And there's a certain factor that relates those two worlds. If an object is rolling, the factor that relates its linear motion to its angular motion is its radius. Delta x equals radius of the tire times its angular displacement. What this means is that as something rotates, it will move a certain distance forward based on the size of the wheel. Bigger wheel, bigger radius means it'll actually roll further forwards based on the same number of rotations as a smaller round object. And I actually I'm going to demonstrate that briefly. I not only have this as an object that can rotate, I also have this golf ball, which conveniently has this black line on it to help you see visually how many times it has spun. So I am going to take these two objects of vastly different radius, and I'm going to rotate them forward by the same amount. First, I'm going to park the golf ball here in this little divot. So this is going to be our starting point. I'm going to do the bike wheel first. And we're going to take this thing through one whole rotation, 360 degrees, 2 pi radians. So I'm going to grab onto this piece of metal here. We're going to spin it around until my hand is back at the top. So one full rotation goes over the edge of that table. And that's 2 meters at least, something like that. It's a pretty good distance. Now I'm going to do the same thing to the golf ball. We are going to take it through the same number of rotations. So, golf ball, note the black line is on the top, and I'm going to spin it through one rotation until it's in the same spot, and we're done. That is the same magnitude of displacement as the bike tire, but only rotationally. They have the exact same delta theta, but their radius is different. Therefore, they rolled forwards by a different amount. If I instead made their linear displacements match, if I just kept rolling the golf ball until it caught up, they'd have the same delta x, but different delta thetas. The golf ball's gonna have to spin several times to keep up. This is one reason why trucks have bigger tires, and so they spin less and wear themselves out less, but it takes way more energy to get them moving. It's also like cars with tiny wheels. If you've ever watched a car or a bike or something with really tiny wheels, or even like a toy wagon, if that object starts going really fast, you can see the wheels like dying, how quickly they're moving. The smaller something is, just the more times it has to spin to keep up. And the same is true for the velocity counterpart and the acceleration counterpart. As long as you know the radius of the wheel, you can turn linear data directly into angular data. And that's what we're going to be doing here. We need to take the linear information that we had to start with and turn it into angular information. And conveniently, we know the size of the tire. So, we know the car's, and therefore the wheel's, linear speed, and if we know the radius of the wheel, we can turn that into angular speed. So, on the previous slide, that information was physically between the two boxes. It's arranged the same way on your formula sheet. I just haven't acknowledged this column very much yet. So they're all labeled transformation, since the goal is to transform linear into angular and vice versa. The velocity one says linear v equals radius times omega. So you can multiply radius by the angular thing to get the linear thing, or you can divide the linear thing by radius to get the angular thing. That's what all three of those transformation formulas have in common. In this case, we can take 29 equal to our radius of 0.33 times our unknown initial angular velocity. And this should give us, if my memory serves, a pretty big answer. No, not pretty big. Bigger. So here we have converted our linear speed of 29 into an angular speed of about 88 radians per second. As long as the car is moving at the same constant velocity of 29 meters per second forward, then the wheels will rotate through about 88 radians every second. I'm actually realizing that the questions on this slide are slightly out of order. Please bear with me. Any questions in finding that angular speed, the angular counterpart? All right. So, next question. How many RPM, which stands for rotations per minute, does this angular speed correlate to? Rotations per minute is another unit for angular speed, like how miles per hour and meters per second are just different units for the same thing, linearly speaking. So we're going to take this and convert it into rotations per minute. So this is a unit conversion. We're not done with those. The relevant, in general, there's two main rotational conversions that you'll have to keep an eye on. I'm never going to hide these from you, but it's still worth writing them on your formula sheet. One full rotation of an object is equal to 2 pi radians. If something rotates completely through, all the way, we say that it has gone through 2 pi's worth of radians, a number of radians equal to 2 times pi. The other conversion is noting that one rotation is the same as 360 degrees. So 1 rot equals 2 pi rad. Likewise, 360 degrees equals 2 pi rad. So really it's just one long 3-part conversion. And occasionally you'll have to make use of different parts of it. In this case, we want to turn radians into rotations and seconds into minute. We're doing this because most cars sold in the United States have an RPM meter that tells you rotations per minute. So we're just gonna see how this correlates to that. It's been a minute. I think it's been a second since I did a conversion on the board. We're starting in rads per second. I'm going to cancel out radians and replace it with rotations. So I'm going to turn this into a fraction where radians is at the bottom to cancel out with this radians on the top. So that would make 1 rotation, which I usually just abbreviate to rot. 1 rot over 2 pi rad. So just turning this equivalency into a fraction in such a way that radians will cancel out. So we need to divide by 2 pi radians to turn radians into rotations. We also need to turn seconds into minutes. If seconds is on the bottom here, I'm going to turn that to a fraction of 60 seconds over 1 minute. Cancel out seconds, leave minutes on the bottom. So this should leave us with rotations per minute. Does anyone disagree with about 840, approximately? Did anyone happen to get about 8,000? Okay. I want to go ahead and point something out. This, I'm fairly professionally confident is the final answer. But sometimes, specifically when doing this conversion, I noticed the issue that pops up in your calculator. If you happened to input it into your calculator like this, then a small problem occurs, because calculators are real dumb. If you did this, or some variation of this, like say did this and then multiplied by 60, what the calculator is going to do is it's going to divide by 2 and then multiply the result by pi, which means that your answer would actually be pi squared times bigger, or about 10 times bigger. So what I usually do just to avoid this is I do it one step at a time. I input just divided by 2 and then divide the answer by pi, but you could also just put parentheses around 2 pi. If you want to do it all in one line. So if you got about 8,000, try that and it should fix the mistake. Again, that's the calculator's fault, not yours. Machines are real stupid. So these wheels are rotating about 840 times per minute. So that's what the RPM gauge on the car means. I don't actually think it correlates directly to the tire's spin. It might be a different part of the rotational apparatus. I'm not really a gearhead. But these wheels are spinning about 840 times per minute. Questions so far? All right. So, the RPM thing is mostly just to demonstrate the conversion. We're going to go back to radians per second because all of our formulas actually want radians per second. So the last question here is, how many radians does each tire rotate before the car stops? So at this point we are hitting the brakes, and we want to know how many times the wheel spins as we slow down. Which, within your formulas, is delta theta. That is the magnitude of angular displacement as the car physically slows down. So, and we already found initial angular speed, so we'll fill that in here. So, this is what we've got, and delta theta is now what we want. So I'm going to turn back to the formulas and we'll kind of choose our path. What we want is delta theta, and there's a handful of formulas in the rotational column that have delta thetas in them. Will this one work for this situation at all? Bless you. This one actually won't work because it inherits the same flaw as this one. This formula doesn't work when you're accelerating. Likewise, this one also does not. And this wheel is definitely accelerating, both linearly and rotationally. It's slowing down linearly and angularly. So this one's out. So let's look at the last two, which tend to be the most useful ones. Delta theta equals omega initial times time plus 1/2 acceleration times time squared. We do know omega initial. We don't quite have alpha. We also don't have time, like at all. So I'm not favoring this one right now for that reason. Looking at number 4, we know omega initial. We actually know omega final too, because we're watching this car till it stops, right? So I actually should write that down as a known. Both velocity final and linearly and angularly, they're both going to be 0. Those are both knowns. So we've got these two. We want delta theta, but we don't technically have alpha yet. We know A, but not alpha. But since we know A, normal linear acceleration A, we can find alpha. So once again, this is a case where we want to convert a linear thing into an angular thing. But I will point out that in this class, there's usually more than one right way to get to the final answer. In this specific case, I'll point out that looking at the linear formula, we have everything we need to find delta x. Because we know linear A, linear velocity initial and final. And if you found delta x, you could convert that into delta theta. So really, I think it's the same amount of steps either direction. There's just two distinct paths. You could either convert everything to angular and do it angularly, or you could solve the linear version and just convert it into the angular version. That's going to be kind of a common trend in these couple of sections. More than one way to get to the right answer, more than one path that you can take. Work it linearly, turn it into angular, turn it into angular, work it angular. So, either or, really, just kind of depends on what you prefer. I'm going to actually do the linear version. Well, no, we need angular practice. I'm going to convert to angular first. So the angular version of the formula is omega final squared equals omega initial squared plus 2 alpha delta theta. We want delta theta, we've got these two, we need alpha first. But that's just the angular counterpart to our linear acceleration conveniently. So one quick conversion, I'm running a little bit low on board space. That transformation formula in the middle says that linear A equals R times rotational alpha. So negative 1.75 equals 0.33 times alpha. And alpha is negative 0.5303 repeating. The unit on that would be rads per second squared. Linear acceleration is meters per second squared. Angularly, you just replace the meters with radians. So that is alpha, which we can now use to find delta theta. So omega final 0, 0 squared is still 0. Omega initial we determined to be 87.88 bracket squared plus 2 times our negative acceleration times delta theta. And your final answer will be fairly large. disagree with about 730 approximately? All right. Again, if you didn't get the same answer, make sure that this is the only thing that gets squared. That would then come over, divide by two numbers, canceling out the negative sign. And that is a lot of radians, but that does still tell us the number of times the wheel spins. In fact, if you wanted to, you could convert that into either degrees or rotations to get a better picture of how many times it actually spins. Because I've been doing physics professionally for at least 10 years at this point, and I still have a hard time thinking in radians, if I'm being honest. So sometimes I'll convert it to rotations just to wrap my head around it. This many radians to turn into rotations, we need to divide by 2 pi, like we did earlier, and that'd be about 116 rotations. So several times on the way to being completely stopped. And again, this correlates to, linearly speaking, the fact that as you slow down while you're accelerating, you do slide forward while that happens. You hit the brake in your car, you don't just immediately stop. It takes some distance to slow down. And so that distance to slow down forwards correlates to the number of times you have to spin while slowing down angularly. Questions, concerns? All right. I would like to very quickly demonstrate the other way I mentioned to get this answer, because if we found delta x, we could just convert that into delta theta. So I want to just quickly prove that that does work. Linearly, that would be 0 squared equals 29 squared plus 2 is negative 1.75 times delta x. Delta x would in that case be about 240. So that tells us that the truck would have to skid 240 meters forwards as it's slowing down. And if we took this and tried to convert it into delta theta, we'd be dividing 240 by 0.33. Which is, wouldn't you know it, about 720 something. So, again, either method works. You can work these sorts of problems linearly and then convert them, or convert first and then do it in the angular way. Again, usually more than one right way to get the right answer. Questions, concerns, anything at all? All right. I do want to briefly practice centripetal force and acceleration also today, stuff that we covered on Monday. One, because it's still what lab this week is about. Two, it's also what Friday is going to be about. So, to quickly review, on Monday, we talked about how sometimes an object that wants to move in a straight line can be forced to move in a circle if a centripetal force is acting on it, pulling it towards the center of an orbital pattern. We see this with the moon orbiting the Earth, or really anything orbiting anything else in space, and also several Earth-bound examples as well. The formulas for that being If a centripetal force is acting on something, it causes a centripetal acceleration on its mass. That centripetal acceleration is equal to either its linear velocity squared over its turning radius, or alternatively, its angular velocity squared times its turning radius. On Friday, we're going to do some more specialized examples about how this relates to the moon and other things moving in space. For today, we're going to look at a more terrestrial example before we break. And look at how jets turn. I already talked about how this affects how cars turn, but it's, again, true for anything that enters rotational motion. So here we have a 2,000 kilogram fighter jet flying at Mach 2. Mach 2 means twice the speed of sound. Speed of sound is 343 meters per second, therefore Mach 2 is 686 meters per second. So very fast, creating sonic booms. And this jet needs to turn. It's moving very fast and it needs to turn at speed. Now the way that jets do this, since they don't have a road beneath them to angle the tires on, what a jet tends to do is it literally just pivots its own body. Because the way that jets and really all planes fly is the wings, when level, generate upward lift. When you tilt the plane physically, that's going to change the direction that all the forces are acting. And between the tilt of the normal wings and a few other tricks, the jet is able to basically take some of its thrust and angle it inward towards the center of a giant imaginary circle. So it's able to generate centripetal force by banking. So the centripetal force, the basically repurposed thrust, is going to pull it towards the center of a giant circle, and it's going to start turning. It wants to move forward and inward at the same time, so it starts turning like how the moon turns around the Earth. That centripetal force is going to cause a centripetal acceleration on both the jet and the person inside the jet. And if I'm being honest, the human is kind of the limiting factor in how quickly this can happen, because humans tend to go unconscious and or die if we accelerate too fast. You might have heard that jet fighters have to go through a lot of training to not black out, like to physically be knocked unconscious while turning too quickly. This is why. If you turn too quick, if the centripetal force and centripetal acceleration on the plane, and therefore your body, is too fast, all the blood can rush out of your head, and then you aren't awake anymore. And then who's flying the plane? So pilots have to specifically train for that, and there's only a certain maximum threshold of centripetal acceleration that humans can even handle in the first place. It's like, if you've ever been at space camp or even on that carnival ride that spins you around real fast against, an outer wall, basically a human centrifuge, that experience was probably like 5 Gs. I believe some pilots have managed to stand 15 Gs before they blacked out. It's not recommended. You're not supposed to go above 10, but upper limits of human potential. 15 Gs means 15 times the acceleration of gravity. That means that humans, hypothetically, can withstand an acceleration of 147 meters per second squared. That's just 15 times G, literally. If anyone ever says like 3 Gs in terms of acceleration, that's 3 times the number of G, 3 times the number of gravity. Here it's 15, and we got a really big acceleration that this pilot could hypothetically withstand. Hypothetically. A lot of people black out before 10. But if this pilot can withstand that much acceleration, I would like to figure out the turning radius of the jet while this person is piloting it that fast. So, this is the maximum centripetal acceleration they can withstand. This is the speed the jet is flying at. We also have the mass of the jet. And I want you to tell me R, the radius of the giant circle that the plane is making in the sky while it's doing this. Give you guys a couple seconds to couple minutes to ponder getting to that answer. Any answers? Yep. So these are our centripetal formulas, and I'm going to use this one because this, representing the max centripetal force a human can withstand, is going to be the centripetal acceleration. That is, again, max the human can withstand. So using this formula, 147, going to equal that top speed over radius. Therefore, radius will be equal to 686 squared over 147, which is about 3,201 and change meters. That's a turning radius of 3 kilometers. If you think your vehicle has a bad turning radius, it might, but this is far worse. And this is really just because of how fast it's going. The faster something is going, the bigger its turning radius tends to be. If you want the turning radius to be smaller, you would need a bigger centripetal force to make that happen, which a bigger centripetal force would cause more force on the pilot, a bigger acceleration on the pilot, and they would definitely be unconscious, assuming they weren't turned into jelly. It's also assuming the plane doesn't just fall apart. It's also why you should slow down before making turns in a car. Questions? All right. That is pretty much everything I wanted to look at today. On Friday, we're going to continue looking at specifically centripetal force and centripetal acceleration. We're going to look back at how on Monday we were talking about the moon. We're going to specifically be looking at the universal law of gravitation and how it acts as a centripetal force in space. And then next week will be some additional rotational stuff, like torque and things like that. Any questions for right now? All right, and if you need anything, have any questions, do be working on the homework, and have a nice day.